Hey guys, welcome back. So let's start with the Packers second lap or third, I don't remember. But then, anyways, this is gonna be a little bit more tricky. You remember we were seeing the UPX one, which is pretty simple, but then we moved to this one, which is ASPack. At the end of the day, guys, keep in mind this is all about methodology, right? We're gonna be practicing the Carnita methodology, which basically means I don't care about you, Packer, obfuscator. I'm just gonna get to the meat, which is the carnita, and just start doing the analysis, right? We really want to get there as soon as possible. So, okay, so let's start. So we're going to have this guy. Let me open it up. Okay, so this guy is ASPack 212, packed with that packer, right? So, okay, so let's start fire up AIDA, and we're going to do the analysis. So we say here new UPX. Here you go. Open it. Obviously, as usual, AIDA is going to say that the import segment seems to be destroyed. It's because it's packed, which makes sense. And then we can see that in the left side we have more functions than than the UPX, which was only I think 2. In this case, it has like 8. We can see the imports. It has also, a few of them. The normal ones, get proc address allows you to get the base address of a API DLL in memory. Get module handle, get the handle of the process. Load library to load a library like a DLL. So basically, those are the ones that the Packer is using for its job. And then if we do Control S, we can see that we have many functions, but as you remember, AIDA is gonna always point to where is the current code located. So we know now that we are executing at ASPack section, and based on the knowledge that we have so far, one of the cases that we saw in UPX is that eventually it's gonna copy all the data unpacked one into the text section and jump there, right? That's a sign that we can always monitor to see if we are kind of getting to the original entry point. Keep in mind that once we are, getting there, we really need to decide whether are we in the Carnita or we are still in the Packer. Because if we are still in the Packer or obfuscator code, we really want to move forward and fast. But if we are in the Carnita, then there is where our real reversing effort starts. Okay, so here a very important thing to mention, even though we don't need to understand everything, as I said, it's just moving fast. This is a very good trick, that very simple but very good one that I want to mention. So you can see here that AIDA has this block in the left side, and then in the right side has another totally different block, right? And they are not connected. So then how come they are here, right? So what is happening, guys, is that here you can see the push A, which is going to basically store the content of the registers into the stack, and another very common command for Packers. And then it's going to do a call. This call is going to call this guy. And let me just put the addresses here in graphic mode by going to general, line prefixes. Now we have the addresses. So we can see that when we do this call, it's gonna actually come here, which is good. It's what AIDA detects, and that's why it does the flow. But then see what happened after that. It do a pop EVP. What pop EVP is doing is gonna basically getting the whatever information is in the top of the stack and save it into the EVP. If you remember our class of reverse engineering, guys, when you do a call, basically what is going to happen behind the scenes is that the next instruction after the call, which is the return address, is going to be pushed into the stack. Why? So that when this call function is done, then the program knows where to jump back to keep executing. But here's the trick. As you can see here in graphic mode, we think that the next instruction of these commands is this, which is not true. Let's go to the sequential mode. Here we can see that after this instruction, we actually have a 07, which is kind of a junk. Then we have 08, which is this jump. and then we have this call that we are seeing in the graphic mode. So what's happening here, guys, is that when we do the call, the push of the next instruction, which is this guy, is pushing to the stack, right? Then we jump here, we pop that instruction, you know, the one that we just push into the stack, we pop it back into EBP, which is 07, increment 1, which is 08, push that value into the stack, and then return. Return is gonna get the top of the stack, which is the RSP pointing to, or ESP if it is 32 bits, and then whatever is that address is gonna take it and jump there. So that's the reason of the trick, right? So basically what it is doing is getting this address, push it into the stack, and jump on it. And that's why we have these different two flows. And actually this second flow, which we saw, is the one which IDA now recognizes as another flow. But because of those tricks, IDA gets confused and it's sometimes very hard to disassemble. Right? This is a simple one, but like that, there are many. Okay, I just want to mention that, and let's see it in action here, guys. So let's do F2. Okay, and let me start the debugger. Start process. Yes, I want to be infected. By the way, this is real malware, guys. So make sure you're running in the VM. Otherwise, they're going to be screwed. Okay, so the first instruction, let me just move the stack here, is going to be the push A. If you check these values, guys, these registers, they're going to be pushed into the stack. So you can remember, for example, 19FFCC. So just for you to check it. So let's see. F7, you can see that now here is the 19FFC, here is the 438001, which is all those guys, right? You can check it out. And you can also even store the flags with push FD. With the F, you also store the flags. Okay, so now we are going to do the call. As you remember, this call is going to push the next instruction, which is 07, after the call into the stack. So we do that, F7. Now we have this instruction into the stack. Okay, we do the pop. We get it now in EBP. Okay, as you can see it here. Now we increment in 1. Okay, and at this point I'm going to return to the graphic mode. And see, we push that value into the stack, which is 438000, which is this guy. So then when we call the return, guess what? Boom, we jump there. You saw the trick? That's pretty cool. This is more like shell coding thing, but anyways, it's pretty simple, but pretty educative. So I really want to mention it. Okay, guys, so now let's start with the Carneta methodology, right? I mean, it's just about understanding the flow quickly. That's why it's very important, if possible, to do the graphic view, because that's going to give us quickly what is the flow. So we can see here that it's going here. I don't care what is going in, what is going on here, what is going on here, what is going here. I don't care. I just really want to see where are the exits, where are the next jumps. So we can see that in the right side we have a return. So we can put a breakpoint here because we don't know if it's going to return to another place, or if, you know, or if it is just going to return back to the previous call. And we have this jump EAX. This jump EAX, guys, is what we call the dynamic calls, which is very important for us because we here, for example, we know that now EAX is pointing to EBP plus 7A, which is a place in memory, and it's jumping there. It's a good sign that this might be the original entry point, right? Because it's jumping to something else. At this point, as you remember, Control S, by doing Control S, we can see the memory space, and we know where we are executing right now. Eventually, it should jump here. Eventually, maybe not. We don't care. The methodology is going to take us wherever is the packer, the obfuscator, and get it done. Okay, so we put the breakpoint in these two sides because we don't know actually which path is going to be taken. So we do play, and we see that we reach this guy. So we do F2 to remove the breakpoint. And the reason I'm going to remove the breakpoint here, guys, and here is because the breakpoint, this is a software breakpoint. When you put a software breakpoint, even though you are seeing this instruction, behind the scenes and the real address at this location is a CC. CC is the opcode to tell the debugger to stop for a breakpoint, right? So what is going to happen is that, I'm not saying this happening here, might be, is that if for example, there is some malware or packers that use the previous instructions to decode or create the next instructions. If that's the case here, what is going to happen that is that instead of having the opcode here, which let me show you quickly, let me add that here so that you can understand it. I want to add here 8 opcodes to show me the opcodes. So let's say that the opcodes here, guys, is FF00, right? Original ones. But when we do the software breakpoint, as I told you, this FF is going to be ZC, which is the opcode of breakpoint. So then if this data that just got executed is used to decode the next instructions for some reason, then what you're going to be using is a CC instead of FF, which basically means you're going to get screwed later because of the breakpoint. The next data is going to be junk. And that's actually a very well-known trick by malware, so that when you are putting breakpoints and you are therefore debugging, they know you're going to put a CC, and therefore they eventually you will just get junk in the next instructions to be executed. So I don't know if that's the reason here, but what I'm doing is just making sure that if that's the case, that's why I'm just removing those breakpoints as soon as I execute them. Let me just remove those opcodes. I don't really need them now. Anyways, so we're here, guys, and then in this right side, it didn't hit the return, and there is something very tricky here, guys, that I really want to point out. So see this return, right? See this push. If you remember what I explained you, right? When you do a push, it's basic and a return, a push and a return. Basically, the return is gonna spec an address, because wherever you are pushing, return is gonna take it and jump there. So, but here we are saying that it is going to push 0 and then a return. That's weird, and actually it's gonna fail, because basically what is gonna happen is that return is gonna try to jump to a 0 address, which that doesn't make any sense, right? Just remember that, because there is a reason for that. But anyways, following our strategy and pretending we don't even know this, we don't even check it, we just put the breakpoints in both sides and we just reach in the left side. Okay, so we do F7 here. It says, hey, the new instructions looks like it was not defined as a code. You want me to treat it as code? Yes, please. Right? We treat it as a code. We get here. I press P to convert it to function, and when you convert it to function, then you can see it in graphic mode. But for some reason, IDA is not converting it to a function here. I'm doing P right now. It's not doing it, and it's because of many reasons. You know, obviously one of them is because of the unpacking. That IDA doesn't recognize it as a function. It doesn't see the epilogue, it doesn't see the prologue in the starting of the function, you know, or the end, and IDA is like, this doesn't look like a function. Anyways, what we can do always is to keep going. The only thing I want to show you guys is if I do Control S, we notice that we are still in that section. We didn't jump here, which kind of tell us that that jump EX probably is not the end of the packer, because we are still in this section. Okay, so here what I'm gonna do is I'm gonna do F7, try to keep executing, guys, and eventually I really wanna keep pressing P. See, I press P here so that it can convert to function. Sometimes it's also a bug. I realize that sometimes IDA interpret it, sometimes not, so it can be a bug because it's the free version. But anyways, I do F8 everything. I don't care about these calls. I just wanna move fast, you know, fast. I just do F8. But see, in this strategy, guys, we don't see the flow, so we cannot move forward with our methodology, right? That's why I really wanna get out of here. I really wanna get into the graphic view. Okay, so let me do P here. Okay, I do P here. Now IDA says, okay, this looks like a function, and as I told you guys, I was just pressing P every time I move on, and suddenly IDA, if you pick it as a function name, then it transforms it into a function, and then the only thing that I really need is graphical view. Why? Because as I told you guys, we really need to move faster. So now here is very clear. It's gonna go here into this jump, then it's gonna get into the right or left. Here is another loop. You know, this loop doesn't take me anywhere. I just jump from there, and you can see, guys, that at the end of this whole thing, we have in this left side we have this jump which take us back, and then we have this right one which take us also back. We double click on it, And the only exit, we are always looking for exits, guys. Remember, either a return or a jump is here. So right away, I put an F2 here. Based on the graphic view, is easy to identify. And then I do play. So we reach here, and I do F2 to remove the breakpoint, and do F7 to step into. Same thing, you know. Either wants to convert it into the code. I want to remove this confirmation so that it doesn't ask us every time. So we jump here. I do P here. Now I treat it as a function, which is great. Now we are here, guys. Okay. Again, Control S. We are still in the same section. Okay. Now, following our methodology, guys, we go here. We see that there is a loop in the right side. There is not another path in the left. We are looking again. Remember, guys, we are looking for exits. So here we have one here. There is there is a block here, and after this block, for some reason, IDA is not doing anything. I don't know if it is because of problems disassembling, but I don't care. I just put a breakpoint here because I really want to move fast. So that's one. So the second one that we're gonna see here is in this side there is loops. There is no returns. There is no calls to dynamic stuff. I mean, these are dynamic calls, but as you can see, after these calls, there is code being executed. So it's not the last one. That's my point, right? So we keep moving. We have these two paths. You can see, guys, it's a lot of information. You don't want to spend time on this obfuscation thing, right? So we get here. We have another block here, which is pop. I just F2 there because I don't know where it's taking it. Then we go to these guys. We have this in the left side is another loop back, and we have this call jumping to something else. So we have these three guys, right, that we identify as an exit, and we just move fast at the end and try to get into the next jump. And keeping in mind that we are still in this area and we are not seeing APIs, we're still seeing these dynamic calls. That is a sign that we are still not there yet. So, but it's always a trial and error, chavos. It's always, chavos means guys, sorry, in Spanish. It's always a trial and error. So I'm gonna click play here, and we see that we hit this guy. Okay, I do F2 to remove this guy, and I'm gonna also remove I'm gonna remove this breakpoint by pressing F2, and then I'm gonna remove this last one because those didn't hit. As I explained before, I don't wanna leave CCs into that data in case it is being used by the packer. Okay, so we are here. We do pop ECX. We do F7, and we jump here. Okay, from there we jump here, which if I do space, you can see that we were here and we just move on here. And IDA didn't show us the next instruction, probably because this was tagged as a start function from IDA, and suddenly you is like, I mean, you're gonna jump back here. It doesn't kind of make sense. There is no return. You know, IDA gets confused. But anyways, we are here. And if you remember, guys, where we are right now, after this whole mess, you remember we put a breakpoint here in the beginning, and I explained you this push, guys. We are right here, okay? So let's see what's going on here, guys. And this is very tricky, a very nice way for them to jump. So EAX, you know, it moves this value, 8419, then it pushes it into the stack, right? Let me increment this. It pushes it into the stack, then it adds to EAX something, which we can see is like a base address. So now we have EAX pointing to 408419. Okay, and then some calculation with ECX, and then we are gonna move EAX to this place. This place, if we don't know it, we just put the mouse over it, and IDA is gonna replace. It's gonna show us where it is pointing to. We can see that it is pointing to the 43842C. Okay. The question is, what is that address? What is this 43842C? Check here, guys. 43842C, and it's gonna move the value of EAX, which is this 408419, which this answers our question that this 0 doesn't make any sense, right? So let's see. F7, we see that it alters this guy, And then when it jumps here, now it makes sense. It do a push of an address, and then it's gonna return, which is gonna jump there. Now we're here, we do P, convert to function, space, and we are now in a new place, okay? Where we are, it's pretty easy. We do Control S, and now see where we are, guys. We are here in this address. Now we are back into the text section as we were trying to, it was one of the theories that it might be coming back to here, right? So we are here. So this is a good candidate for us to dump it and get the original entry point, right? So we're gonna do that. I'm gonna copy this potential original entry point. Okay, I do copy, fire up Zilla x86 version, because this is a 32-bit binary. We found our processing memory. We tell them, hey, look up for the address table in this area. It says I found it. We get the imports, and we can see that it gets kernel 32, but it gets way more APIs than before, which is a good sign. So we dump it. As you remember, guys, this dumping function in Zilla is great because you don't need to have a external plugin to do the dumping like before. So we save it, we do the fixed dump, choose the dump that we just did, and that's it. Now let's open it with IDA. We open a new instance. Okay. We open this guy, which is the one that we just fixed. Okay, we can see in the left side looks like it's kind of the same number of functions, but in the imports we can see that now we have way more imports functions, APIs. Sorry, more APIs than before. Okay, which is a good sign. Now here, guys, we can see the same flow that we are seeing in the debugger. Just one thing that I want to really point out is that here we can see these APIs, which again is a good sign, guys. Remember, when you start seeing APIs different than memcpy, different than HIPAA lock that are just for copying here and there, when you start seeing APIs like this one, right, like delete mount point, that doesn't have to be anything related to packing. It looks like it's a function trying to do something, right? So that tells you that this looks like is malicious code, right? It's actions by the malware. It's the carnita, okay? So that's a sign that you are in the right path, okay? Another thing that I want to really show you guys here is that we can see the APIs very clear. And let me show you how those looks in the memory right now where we are debugging. If we go down to the same area, because it's exactly the same, we can see that right here, we have the TLS alloc. You can see it, TLS alloc. And then right here, we have this delete volume mount point. First of all, you can see that here is kind of difficult. And it is only 2 APIs, right? These two. But what if you have 30, 40, right? So that's why dumping it is a very good recommendation. And you can dump it anytime, right? If you are hesitating, if you are already in the carnita, in the data of the malicious code, just dump it and open it. Oh no, you know what? It's just loops and loops and loops. Okay, let's move forward, right?